All right, this is our second QQT from Unit 4. So I have a block on the top of a ramp, and it's going to slide down that ramp and then come to a horizontal section and eventually come to a stop. We're told that friction is negligible on the ramp, but as soon as it hits the horizontal section, there is friction with that given coefficient U sub B. So what we're going to do is we're going to graph for part A. We're going to graph the kinetic energy of the block and the gravitational potential energy of the block from x equals negative d to x equals d. So the graph on this whiteboard doesn't work as well as I would like it to, so I'm just going to freehand this. It'll work. Here's minus d, here's d, 1d, 2d, 3d, and 4d. Okay, so let's start with gravitational potential energy, and I'll do that in black. So gravitational potential energy starts at a maximum at minus d. So it tells us that we don't have to label the graphs, but the vertical axis needs to be consistent. And that'll make more sense when I talk about kinetic energy. So it starts at a maximum. At x equals 0, the gravitational potential energy is at a minimum. So that point is here, okay? And then gravitational potential energy is 0 between x equals 0 and x equals 4d, so it's going to look like that. So the question is, what's that graph going to look like between minus d and d? And so we can tell that from our formula. Gravitational potential energy as h decreases, and h decreases as x increases in a linear fashion. So we have a linear relationship here. That should be a straight line, okay? And so that's what the gravitational potential energy looks like. Now let's talk about the kinetic energy, and I'll do that in green. And I did the wrong thing, sorry. K equals half mv squared. But what we know is that in order for energy to be conserved, and since there's no friction on the ramp, we're not losing any energy, the total amount of energy is the same at all times. So we know that kinetic energy starts at a minimum at x equals minus d because the block's at rest. It's going to be at a maximum at x equals 0. So this graph is actually going to be linear like that. Now, I got sucked into thinking I was going to graph the velocity, and I did a quadratic, but then I realized that's not right. We're just looking for energy. And so it's even Steven. As UG goes down, K goes up, the total amount should be constant at all times. So this just looks like an X. Both of those are supposed to be straight lines. If I were doing this, I would use a ruler. But so what happens to kinetic energy after it hits the rough ramp? Okay, it's going to decrease because friction is going to do work on it, right? Because we know that work will change its kinetic energy. Well, the work done by friction, I guess I'll call that the work done by friction, is the force due to friction times the distance, right? And this is mu k times what would be mg times the distance. So this is also linear in d, with this being the slope. So eventually it's going to be 0 at 4d because that's when it stops. And then I want a straight line, that wasn't great, but it's linear there as well. So that's what the graphs of those two things look like. The rubric for this is 4 points, okay? 1 point for either curve with a reasonable shape between minus d and 0, with the maximum and minimum in the right place. So if you figured out the max and min either of u, g, or k and drew a straight line between x equals minus d and x equals 0, you get that point. 1 point for two curves from minus d to 0 such that the total energy is constant. So if you realize that the total energy was constant, even if your curves are not straight lines, you can still get that point. 1 point for realizing that gravitational potential energy is 0 from x equals 0 to x equals 4d, and 1 point for realizing that kinetic energy is linear from a maximum at x equals 0 to 0 at x equals 4d. So 4 points for part A. All right, part B illustrates a couple of things. One, it illustrates how useful the factor of change method can be, and it also illustrates how you can sort of back your way, make two mistakes, but get the right answer. However, that won't necessarily get you all or any of the points on this test. So B says the block is released from the top of a new ramp that has a base length of 2d, but still makes an angle theta with the horizontal. Student is asked to predict where the final horizontal position of the block will be twice as far from the base of the ramp compared to when it was released from the original ramp. The student reasons that since the block will be released from a new height that is twice as high as the original height, the block will have more energy when it reaches the base of the ramp, so it will slide farther along the right surface before stopping at a position x equals 8d. So it's probably pretty obvious that the first part of that reasoning is correct. Since the block will be released from a new height, the block will have more energy when it reaches the base of the ramp, so it will slide farther along the right surface. That part we're sure of. The question is it really 8D? Because we've been fooled before. So let's look into that. So we know the block will have more energy when it reaches the bottom, but will it be twice as great? Well, let's see. We know that the energy will be twice as great. What we have when we have mgh at the top and half mv squared at the bottom, we've done this before. We get v is equal to rad 2gh. Okay, so my new velocity, if I'm going to drop from twice as high, is going to be, by factor of change, a 1 here, a 1 here, and a 2 here. So that's square root of 2 times the old velocity. Okay, how much kinetic energy is it going to have? The new kinetic energy, right? Or I should start with the formula, K equals half mv squared. The new kinetic energy is going to be 1 for the half, 1 for the mass, rad 2 for the velocity, squared, excuse me, so that's 2 times the old kinetic energy. So the new situation, the block's going to have twice the old kinetic energy. Why do I care? Well, because how much kinetic energy it has determines how far it's going to slide, right? So the new work is going to be equal to, the new work is going to be equal to the new kinetic energy, which is twice the old kinetic energy, right? So that's going to equal FD. We know that the frictional force, right, which is just equal to mu times the normal force, none of that's changing. So if the kinetic energy changes or doubles, the distance is going to double. So the new distance will be 8d. So 1 point for saying that the more energy after falling from the new ramp is correct. 1 point for saying that the new distance will be 8d. So 2 points for part BI. Part BII asks what part of the reasoning is wrong, and the answer is none. Everything they said is correct. So that's part B. Okay, part C asks us to derive an equation for the new final position of the block. So let's talk about the first ramp here. We had, let me just draw it really quickly here. Here's theta. Here's the height it was dropped from. Originally this was D. Okay, so what we have here, we have mgh equals 1/2 mv squared, which then equals the frictional force times x, and x is the distance that the block is going to travel before it leaves. Okay, so a little bit of manipulation here. mgh equals mu k times mg times x. The masses cancel out, but we need an expression for h. Okay, so looking at this triangle here, the tangent of theta is equal to h over d. So h equals d tangent theta. And we can use d and we can use theta because d is remaining constant. No matter how the block is moving, that d is a fixed length, and the theta is a fixed length, which we've been told before. So I can plug this h equals d tangent theta into here, and so I get an mg d tan theta equals mu k mg, and then the original x, right, and the original problem was 4d. Okay, that was the original distance. So a little bit of canceling gives us tangent theta over mu k equals 4. I'm not entirely sure why I did that, but I do now, because we got to draw the triangle for the new situation. So I'm going to circle that and go on to the next ramp. The new ramp, this is now 2d, right? This is still theta. Here's our new h, okay? Our 2h, excuse me, because we just doubled both sides to keep the angle the same. So we have the new ramp, mgh equals mu mgx, okay? Our new h is 2d tan theta, tan theta equals mu mgx. So x equals 2d. And remember, tangent theta over mu k was 4. So I guess we could say that tangent theta equals 4 mu k. Either way, 4 mu x, and then the mu's still over here. However you do the algebra, the mu's cancel out, and we get x equals 8d. Now that seems like a long road to hoe to get that answer, and if anyone had a more elegant solution, I'd be happy to hear that. 3 points for this. 1 point for realizing that the initial energy in the Earth block system is twice in the final ramp. So realizing that this was mg times 2h. Okay, we get a point for that. For realizing that in order to keep this angle the same and to double the length of this leg, we have to double the length of that leg. Okay, 1 point for realizing that the frictional force remains the same. All right, Fk is equal to mu k times the normal force. I don't care what else happens there. 1 point for equating the initial gravitational potential energy to show that the energy dissipated is proportional to the distance that the block slides. So this right here, saying that mgh is equal to the frictional force times x. 3 points for that. So that was a long problem. I apologize for the long video.